All right, so this is going to be the idea that kind of ties things together. And I tend to do it from a life viewpoint. As we started out this class, more of a how you got here, what this means to you viewpoint. Um, Astronomy was a very important subject. It helped set time, and by setting time, we could make our first predictions, especially about important things, growing seasons, animal migrations, things that mattered to people. Um, but the consequence of it is we learn place, and it has very strong philosophical, cultural ramifications. Learning place led to navigation. We use the stars to navigate. You still, if you do outdoorsman activities, um, navigating by the stars is a skill that's still taught. Um, Basic navigation where the sun is, right? East, west. Um, this learning of place tends to have some blowback. Um, it is in, in the scale of astronomy, in the scale of the distances between our Earth and the sun and the rest of the stars in the Milky Way galaxy, and then all the galaxies in the local supergroup, and then all the galaxies in the universe, we are incredibly small. And I don't know, I think we have an idea that size relates to worth. Take that as you may. I mean, no humor by it. It does seem to be a human condition that the larger things are, the more valuable they are, the more powerful they are, the more. But we also have an economic viewpoint of worth, which is the more rare something is, the more valuable it is. And so I take the context that in the depth of this really, really large universe, both in time and space, our fragment of time and space that we occupy is rare, completely unique, and more precious than anything else. But the size scale does hurt people. It's hard to imagine some of these distances sometimes. And so we have a tax. There's a huge rise in people that believe the Earth is flat again, because we're being taught not to trust any institution's information it gives to us. And since you can't see the Earth is round and you don't trust the information of institutions, you assume that that's false, and it makes sense that it should be flat. Um, so, that being said, we're going to talk about some really big things both in space and time, and most people question their place there. I'm going to talk about how astronomy has worked in finding place in this. So, here's our first goal here. For some reason, this is smaller on this than it is on the big screen. Oh well. I'll get to the main information. So, we orbit a star that's in a Milky Way galaxy. Our Milky Way galaxy is 150,000 light years across. We found it was bigger in the last few years. So the light takes 150,000 years to go from one end of the Milky Way galaxy to the other. Our solar system is about 26,000 light years from the galactic center. 8 kiloparsecs we are from the galactic center, so we're close to the center relative to the size of the galaxy. And we travel around a huge black hole in the middle of that galaxy. It takes us 250 million years to orbit once around our galaxy, but our galaxy is in a group of galaxies, huge small galaxies falling in, colliding with us, which is called our local group. The Andromeda Galaxy, which is about the size of 3 moons in the sky, but so faint you can barely see it with the naked eye. It looks like a little bit of smudge, comes out a little bit better in a telescope. Is our nearest large galaxy neighbor of the local group. It's part of a group of galaxies called a supercluster, and then in the Virgo supercluster, which is part of a larger supercluster. And these galaxies are 50 million light years away. So the light is taking 50 million years to reach us. And so that's our local area. Now, for context, right, we orbit one star. Well, each galaxy has billions of stars. And so we're talking about billions of things like ourselves. And this is usually the size scale that's used to show this. Here's Earth, and Earth in the solar system in the Milky Way, the Milky Way in the local group in the local supercluster, and then the whole universe. Whoops, those buttons shouldn't have been doing that. And so if we want to kind of look at the size of this, this is if they put this on the size of different buildings. And so what they did is they put the sun and the planets in the Voyage model, which I believe is in Washington, D.C. And they go to the National Air and Space Museum and they map out where the planets would be. And so we use the National Space. And so if the sun were in the middle, and then Saturn would be here, and Pluto would be out at the Art Industrial Building. Of course, if you haven't been to DC, this doesn't make much sense, right? Normally, what I tend to like to do with this, and there's different ways you can do it. So as I like to take a soccer ball or a basketball and make that the sun, and then go or an orange, depending on how much space you have, and say if that was the actual size of the sun, where all the planets would be, and you end up walking across multiple football fields worth of length to get it. This is the planets compared to the size of the sun. We're very small compared to the size of the sun. That's only a quarter of the sun shown there. And the planets coming across. So we have very small things spread out through a very vast distance. And that's just locally. Our galaxy has us orbiting here. And again, that's about 26,000 light years. And from here to here is about 75,000 light years. So we're about a third of the way out, a little more, from the center. And we orbit this way around. And there are lots of stars in the disk. And then there's this bright region in the middle, which is the bulge. And then there's stars that kind of, not many stars, that kind of orbit in random directions in the halo. Everything in the disk is going in the same direction. And everything in the halo is kind of random. But that makes up our galaxy. And so from here to here, it's about 150,000 light years. It says 100,000 here, but new evidence has suggested it's larger, and there was kind of a warp in the things here, so it looked like it ended, and a warp down here that looked like it ended. And if you take care of that warp, you get about another 25,000 light years on each side. So our galaxy is pretty big. And again, light year is how long it takes light to travel in a year. So the light from the sun to the Earth takes 8.5 minutes, which is 93 million miles. Light years, the nearest star to us, takes 4 years for the light to reach us. So space is pretty empty, but things collect together with their gravity. All right, if we look out in really, really bright, and we look out in every direction away from Earth, this is what the Milky Way galaxy looks like. So we're looking in towards the center, and then in all the stuff around us circles around us, right? Because we're in the middle of something here, and here's the center. And this is what the Milky Way galaxy looks like. If we look at really high energy things, if we look at infrared light or heat, we get this viewpoint. but there's this definite collection of matter that makes up our galaxy. In fact, collection of matter, it tends to be what it is. This is what it looks like in visible light. And if you go out at night, you can see the Milky Way. Though it doesn't come out in this good of colors, it is definitely milky in color. And washes the sky. And that's just the nature of the human eye. These things are so faint, we don't get the color as much as we get the intensity. All right, and here's looking at the Milky Way, counting the number of stars. And so where this gets darker, there are more stars. And so we're looking at stars in the Milky Way, again, looking out from us. Here is an idea of the universe, focusing similar to that previous map. This is have this up in the wall of my office. So National Geographic did this when we first started measuring some of the superclusters. And so here's our solar system. Here's our nearby stars in the Milky Way. Here's the Milky Way and its satellites, the things that are orbiting the Milky Way, other galaxies orbiting the Milky Way. There's the local group. There's the supercluster. And then in the background, what the general universe looks like. So the universe is huge, right? This is a map of all the galaxies seen. This was the Great Wall. The scientists got really, really scared when they found this because they thought there might be a wall of galaxies, like an actual end of galaxies. I wouldn't say that that's what they thought, but there just seemed to be this ring, and they were wondering if there was something that was producing galaxies at the edge. But then as our telescopes got better, we saw more, and we tend to see that things cluster in filaments. Galaxies cluster together. And that's gravity. Gravity doing its job, pulling things together. And there's actually regions in the universe that are completely empty. Completely empty. Most of the universe actually are these regions of complete emptiness. Just most of the matter tends to clump together. So these regions of complete emptiness are dark, and empty. Many, 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 many millions of light years across, with nothing in them. I think the term for them right now, they're called bubbles. And so here is if we made a simulation of where all the matter would be and how things cluster together, and we run that simulation, the universe would look like this. And this is a simulation on how gravity works with dark matter, matter that doesn't emit light. And so if we run that simulation, the universe looks like areas where the matter condenses and areas where there's no matter. Well, that simulation matches what we see. We can see those kind of fibrous clusters here and then those empty spaces, right? Of course, this is three-dimensional, so it's kind of like a spongy collection of matter spread out. All right. So we can only observe as far as light can travel. So the size of the observable universe is limited by the age of the universe. And the age of the universe is about 13.8 billion light years old. If we take into account the fact that the universe was expanding, and so since the time we've seen that light, the universe has gotten wider, the universe expands, then in the universe, the radius of the observable universe is about 46 billion light years. So now, science is going to say this thing, if you can't observe it, it doesn't exist, or at least it doesn't affect you. So even though our universe may be infinite, or it may be finite, we're within a part of it that the parts that affect us is only 46 billion light years in a radius around us. Anything further away from that, the light would never reach us. No matter would reach us. No energy would reach us. It wouldn't do anything that would change what happens here. And we couldn't change what was there. We're effectively cut off from it. Some people liken this to it as like being inside a black hole. And that's our event horizon. And there are physicists that are looking like, well, is the fact that we see the universe expanding mean that we're inside a black hole? And there's no way to prove or disprove that theory yet. So we might be inside a black hole that makes black holes, which is even a weirder thing. Well, so what happened is Einstein in 1915, exploring gravity, came up with general relativity. Now, different people explored the equations of general relativity and realized you were going to have one possibility. The entire universe would suck back in on itself because gravity is one directional, it pulls in. So Einstein made a correction to that. He made a cosmological constant that there was something in the universe that pushed out on everything. But he wanted the universe to be stable. He didn't want anything to fall in on itself. And so he assumed that this constant was in constant equilibrium with the universe. Well, people solved the different equations to this and found that there was a possibility that the universe could have started in a singularity, in a small point, where all the matter in the universe was in one place and it was expanding outwards. And this eventually got called the Big Bang Theory. There's really no Big Bang to it. It's not a huge explosion. It's the universe is expanding, and as it expands, matter starts doing these neat energetic things. Einstein was initially against this theory because it was really first articulated by Lemaitre. I'll have to look up the name pronunciation again. Who was a priest, and he thought that this point of the singularity where everything was gave a convenient point of creation, and so he thought that you were trying to mix religion and science. Which is odd because Einstein's own idea that the universe should be stable was mixing philosophy and science. And you have to rely on what's observed. And Einstein was humble enough to do this. Hubble found and measured and was able to measure that all the galaxies are moving further away. By observing them and observing how their light shifts, he could see that the galaxies were moving further away. And that led to us measuring the Big Bang Theory, or the Big Bang as we see here. And so what happens is all of the matter in the universe starts here. And then very, very quickly, in the first 10 to the negative 32 seconds, or very small fraction of a second, it expands very quickly. It gets very large. And as it gets larger, all the matter that was stuck together starts clumping, and it forms distinct things. And so in the first microsecond, we start getting protons. And protons are what develops elements. And in the first 100th of a second, these protons are forming. And so really you have a universe that's nothing but hydrogen and subatomic particles, because one proton is hydrogen. And from that 100th of a second for about 3 minutes. So what, 2.99 minutes, or not 2.99 because it's a 10th of a second. So what would it be? 2 minutes, 59.99 seconds. The universe starts fusing protons together. And it does this, and it produces only 4 elements of the periodic table. It produces hydrogen from the protons, helium, lithium, and beryllium. And that's it. Everything in the universe for the first 3 minutes is made of those particles. Now the particles are so close, because the universe is so close together, that any light that gets produced is immediately absorbed by a neighbor, and so the universe is opaque. You can't see because any photons are getting absorbed by electrons. Any energy is getting absorbed. At 380,000 years, it finally expands so far apart that the light can escape. And when it does that, that means that every time an atom would try to grab an electron, it would get hit by a beam of light, and the electron will get knocked out, just like the fluorescent lamps are working. And this was happening over and over again. So these atoms were all ions. They are positively charged, and the electrons are floating around freely, getting bombarded by light, always having too much energy to rest inside of the atoms. And so this line is called the ionization of the universe, because what happens is as soon as you get far enough that light can go out, electrons can lose enough energy that stable atoms can be formed, or neutral atoms can be formed. And so neutral hydrogen starts forming right after that, and light escapes out. Now that light is called the cosmic microwave background radiation. That light exists everywhere. If we look everywhere, that light is there. And that light was very, very high energy. The universe is very hot at this point in time. But as it expands like a gas, it cools. And so that light cools down as the universe expands. And so when we go to look for this light, we actually have to look for something cool. And the universe continues to expand. And so that's the picture of the radius of the visible universe as time goes on. But notice, the only thing that can produce elements is this initial fusion. And so this initial fusion only produced 4 elements: hydrogen, helium, beryllium, and lithium. And so Hubble, the one that measured the universe expansion, showed that all galaxies are advancing away, and they advance away from each other more quickly the further away they are. This is very, very similar to if you draw dots on a balloon and blow up the balloon. All the dots on the balloon will get further and further away from each other as the balloon stretches. And if we look and observe galaxies and faraway stars, we can see them all moving away, and the further they are away, the quicker they're moving away. There's been many, many surveys to do this. The Sloan Digital Sky Survey looked for supernovae to measure the rate that galaxies were moving apart, and we have a fairly good idea of this expansion. Well, so all the universe can produce are 4 elements: hydrogen, helium, beryllium, lithium. But I know I've got some carbon, right? Carbon's the mechanism of life. And I look around and there's definitely more than just 4 elements making everything up. And so to look at that, we have to look at the next thing the universe starts producing. And so once all of this matter is squished together really, really tight and it starts expanding out, well, gravity's going to want to clump it together. And the first major thing it clumps into are galaxies. And galaxies are a collection of all this stuff that's being produced, right? So it's all this stuff, we could kind of think of it as gas. And these gases get clumped together. And this clumping together of these gases start forming stars. And so we're going to look at different types of stars. And we talk about stars as being low mass stars and high mass stars because different things happen. And so a low mass star is like our sun, which is about 2.5 our sun or less. And they have a surface temperature that's about 8,500 kelvins. Our sun has a surface temperature about 5,700 Kelvin. I've noticed now if I go into Home Depot and look at lights, they'll actually give the temperature of the light being produced. What determines the color of the light is the temperature. And so the lights that try to mimic sunlight try to have a 5,700 Kelvin peak. So this is going through what, and the color of the stars will actually help us determine their temperatures. Well, inside of this star, all the hydrogen gas, and that early Big Bang process producing those 4 elements, about 88% of it was hydrogen, more than 88% of it. The rest was mostly helium. The lithium and beryllium was barely produced. And most of the universe is hydrogen. Hydrogen gives off a pink color. And if we look at the spectrum of the universe, it has this pinkish glow from the different radiation emitted by hydrogen. So gravity pulls all of this hydrogen together and forces the atoms close into each other, which is a process called nuclear fusion. And nuclear fusion helps synthesize new atoms. And so what happens is uh, two hydrogen atoms come together, producing a hydrogen and a neutron, and a hydrogen. And two over here produce a hydrogen and a neutron and a hydrogen. Or this would be the idea of um, deuterium, which is in heavy water. And so the hydrogen produces these two particles, right? The energy of crushing them together creates a neutron, really, comes out of this. Now, these new particles come together to form a helium plus some gamma radiation. And so this is happening inside the sun. It's actually happening slowly and methodically. There's just a lot of stuff in the sun. The energy wall needed to crush these atoms together is really high, and it's a rare random event. But because there's so much stuff in the sun, it's happening really regularly. And that poor little gamma ray goes racing out, trying to be visible light, and it gets absorbed by all the atoms between the inside, the center of the sun, and the outside of the sun. And so the journey for a piece of light to get out of this energy process through the sun is a multi-million-year process. It's getting absorbed. The light we actually see is the heat on the outside radiating away. This nuclear reaction in the middle produces different byproducts that have to fight their way through all the atoms to get out of the sun. So it's just a really, really crowded. And you look at these little charts and you're like, oh, well, yeah, a couple things come together, this stuff shoots out, it's great. But what you have to think of the sun is pulling all of this stuff together. We say it's a gas, but it's a dense, thick miasma of plasma. If we grow, they might be giants. This stuff just being pulled together thicker and thicker and thicker because the gravity is pulling it closer and closer together. This syrupy molasses of high energy individual particles that are getting crushed together. But look, two different things give us a new thing. And so the sun is losing its fuel. It's burning its fuel. Just like when you burn a piece of wood and you start burning away parts of it, the parts burn away, right? A chemical reaction in the case of wood carry the oxygen and the carbon and react, creating CO2, which floats away. And so the carbon leaves and you're left with an ash. Well, at this point, the hydrogen is going away and you're being left with helium. And that's what low mass stars do. Eventually that hydrogen core is going to go away. And it'll all be helium. That's about 5 billion years for our sun. So if we want a timeline of things happening here, right? Our sun was created about 5 billion years ago. It's got about 5 billion more years to go. When that happens, the pressure, those gamma rays coming out, and all of the energy being released stops happening. And so gravity, the only force will be inwards. And so the star will collapse. Right? So gravity's pulling this all in to mix it together. It's releasing energy that's fighting to get out. And so when I try to describe these, this is like countering processes. Gravity's pulling in and the energy's pushing out. So the star's kind of in an equilibrium. It doesn't want to fall in. When it runs out of fuel, and you'll see this is the story of stars. When you run out of fuel, gravity wins, the star starts to collapse. And the collapse causes the hydrogen around the core to compress. And so this was all happening at the center, but now we only have helium in the center. But this collapse puts a little more energy outside of it, and they begin fusion. But because it's not contained in a core, it escapes really quickly, and the star balloons out to a huge radius. And this is called a red giant. And red giant stars, or they're red giant branch stars, are stars that have stopped hydrogen production in the core. They collapse, and then they have hydrogen production in their outer shell. Now that 100 times the size of the radius, we think our sun in about 5 billion years will expand to where it will be the size of the orbit of maybe Mars, right? Maybe not quite Earth, but still really close to us. And so this keeps producing helium, and about a billion years after that, the core gets big enough that the helium starts to fuse. So it can't produce enough helium to start fusion right away, but as the outer shell produces more helium, eventually it adds up enough helium and it starts producing helium. Now the helium plus this barrel fuse, and it's kind of without the presence of this, you don't get this production, which is why it's lucky some of it was produced early on in the universe. The core temperature goes way high, which creates a lot more energy, which starts this fusion. And 3 helium nuclei fuse together. 2 of them form the barrel, and then in the barrel, the helium produce a carbon. So notice here's, again, it's a 2-stage process, just like the hydrogen produced the deuterium and the hydrogen. Here 2 heliums produce a barrel, and then another helium comes along and produces carbon. And notice this is the first entrance of carbon into the universe. Right? Before then, the universe didn't have the material to make carbon. So if I'm made out of carbon, that carbon had to be made in a star, since the universe doesn't produce it. But I'm also made out of water, which is hydrogen and oxygen. So the hydrogen was produced by the Big Bang. So parts of me were made in a star, and parts of me were made in the Big Bang itself. Oh, that's kind of cool. And so the beryllium-8 nucleus produces carbon-12. These probabilities are very low. The beryllium-8 really favors this interaction and increases the probability of it. This slide here, and I'll just give it a second. One of the problems with science sometimes is this is called the anthropic principle. And when we look at the universe, the chances of life happening are statistically impossible. But here we are in life. So it has to be probable. And this nuclear process, no one could mathematically figure out how to happen. It was extremely improbable, so there had to be something for it because we saw it happening. And because we saw it happening, we knew there was a rule for it. We just didn't know why. So you go, well, it should be this. Right? You go, because I see this happening, it has to have something like this. We'll make that thing, and then we'll look for that thing. And that's very common in science, is we exist. Something has had to lead to our existence. And so we go, well, what is that something? We'll say it's this, and we'll observe to see if it's true. And if our observations prove it, it comes through. And Hoyle did that with finding the beryllium-8 to form the carbon. There was no way it could happen with just the helium. There was just not enough energy. So you needed a material that had that energy. They found it, and then they figured out how it was produced. They kind of worked their way backwards. All right, so this helium fusion continues until the fusion just runs away. It produces 100 billion times its normal energy really, really quickly. Just builds up enough material, and all of a sudden it does this thing called a helium flash. Think about it like you get too much air to a fire, and it'll do a really quick burst because it has enough oxygen to do this chemical process really quickly, but it burns up all its fuel. And 60 to 80% of the helium in the star is consumed and turned into carbon. The process occurs in the core, and the star remains intact. And then you have a carbon core and a layer of helium outside, which it undergoes a slow fusion to produce more carbon. This helium layer has what little hydrogen is left outside of it, producing helium, and it just slowly does the shell burning, and the outer layers expand further and further and further, and this is called an asymptotic branch star. But it's different than the red giant. Its shells are burning, and the core is a chunk of carbon. Notice there's not enough energy for the carbon to burn. Low mass stars do not have enough gravity for the carbon to turn into anything else. And so the burning on the outside of the stars will slowly break down, and it becomes what we call a white dwarf star. You'll hear some people sometimes talk about white dwarf stars as kind of being like diamonds, because if you think about it, a diamond is carbon, nothing but carbon, coal, under huge pressure, and that's what the core of these stars are. You know, whoever did the Twinkle Twinkle Little Star words got it right. The white dwarfs become carbon chunk that's almost is perfectly crystal. And most stars in the universe end up being a white dwarf. That's what happens. They have about 10 billion years, and then they turn into a white dwarf, glowing from the leftover heat and what little nuclear fusion is on the outside. All right. Well, if you have more than 2.5 times the mass of the sun, you have enough mass to squish your innards more. And so you can start burning carbon. So the other cycle happens. The cycle that we talked about before, the hydrogen burning and the helium burning, happens. But then when the helium burning ceases, the carbon can actually burn. And we have this carbon, nitrogen, oxygen cycle, where these stars just start producing carbon, nitrogen, and oxygen in a complicated cycle. But notice we've introduced two more elements. You know, nitrogen and oxygen. We've got two more elements being created in these stars in this complicated cycle, this CNO cycle. And notice hydrogen is needed, gamma rays come back forward, more hydrogen is needed. So the hydrogen, you still need this large quantity of hydrogen coming in, some helium comes out, and you have this production chain that keeps coming about. Eventually, you get an internal carbon core surrounded by a helium layer and a layer of hydrogen. But the energy is enough to start carbon fusion directly into neon. And that's only going to last for a few hundred years. Notice we were talking about billion year processes. One of the things that happens is the larger the star is, the more energy gravity brings. These things don't live as long. I guess what you have, the brighter you burn, the less you live. And so the more mass you have, the larger of a star you are, the shorter your lifetime is on. And so this carbon runs out, and neon fuses to produce magnesium and oxygen. Neon fusion ceases, the core collapses a little bit further. Oxygen fuses, producing silicon. And each of these steps take shorter and shorter times. But notice these nuclear reactions are starting to create more elements in the periodic table. The gravitational pressure of large stars starts turning carbon into magnesium and oxygen, into neon, and then neon into magnesium and oxygen. Neon stops producing, the oxygen starts fusing, producing silicon, which is most of the Earth, right? The Earth, large silicon oxygen is like most of the material in rock. And it gets quicker and quicker and quicker and quicker until silicon results in the formation of iron. And so we end up with a star that looks like this. It has a core that's iron. Outside of that is silicon, then magnesium, then oxygen, then neon, then carbon, then helium, then hydrogen, and then hydrogen that's not burning. But because of the energy requirements to fuse iron, it sits on the boundary where heavier elements break up by fission and lighter elements come together by fusion. Iron is kind of the halfway house. It's not going to allow any more fusion. But these shells are collapsing in as energy stops. And so almost the moment the iron core gets created, these shells start collapsing. We get core collapse. And so the iron is no longer undergoing fusion. There's insignificant pressure pushing out from gravity. And the gravity is so great that the electrons are driven into fusing with protons. They make neutrons. Right? I think I told you earlier that if a neutron were allowed to sit around, it would spontaneously break down into a proton and an electron. Well, in this process, the star's gravity slams the electrons back into the protons, making neutrons. And the star collapses to form a neutron star, which is just a few kilometers in diameter. But an enormous amount of energy is released. It blows away all of the outer layers in a supernova and releases so much energy that very, very distant stars can be seen. We can see supernovae in other galaxies. They get that bright. They can release so much radiation in the form of light from collapsing. All of the mass on the outside gets blown away and only the core is left because the gravity is so strong and this neutron production is so strong. And it's in that explosion that the rest of the elements get made. So one of the really weird things about stars is they can only make things up to iron. You can't make gold, you can't make copper. Can't make loads of the things that we see, and they actually kind of do it in a mathematical way that it was only those things that we saw in the shell here they can make. Stars can only make iron, silicon, magnesium, oxygen, neon, carbon, and helium. Hydrogen comes from the universe itself. Nothing makes any more hydrogen. It was there in the beginning of the universe, and when hydrogen atoms get destroyed into individual protons, well, that's its very long process, but then matter goes away. But the creation of new elements, stars can only create these things. Well, we saw on the periodic table, it was huge. Well, when the stars explode, they create everything else. And if we look at the elements and how much of them are in the universe, we see the things that are produced in the cores of stars up here. Hydrogen, helium, carbon, oxygen, neon, silicon, iron. Things produced in the core are the most abundant things in the universe. The things that were produced in the Big Bang, the most abundant. Everything else falls down, and this is staggered. This is a log scale, so every dip down is about 10 to 100 times less the amount. So the things that the stars produce in their cores are this upper curve here. Everything below that are produced in the explosions of stars. And I'll leave lithium and beryllium out of it, or lithium and beryl, because these are produced in the Big Bang. These two here. In fact, you can really say Big Bang production starts here, and then inside stars does this upper bit here, skipping over to here. And these large stars produce and explode to produce all these other things. And so in the explosion, the other elements come out. Now, we can look at our stars and how they work in a thing called a Hertzsprung-Russell diagram. This is a really animated one. Did I put my simpler one in here? No. It shows where stars fall in with their color versus their luminosity, or how bright they are. And the color is a relation to temperature. And what tends to happen is stars work their way into the main sequence, and then when the end of their life, they come off the main sequence and track through. So our sun would have tracked down into its position here, And then as it ages, it doesn't move up or down the diagram. It mass fix it into a place on the diagram, and it'll pop off into a red giant phase, pop over, and the different burnings, and it'll push out here to the white dwarf phase. If you start with a different amount of mass, you'll come onto the main sequence here, you'll exit into the supergiant phase, and then maybe end as a neutron star or a black hole. Whoa. And so we're able to classify stars. The key that determines how a star lives, its kind of genetic lifespan, is the amount of mass that forms it. And the amount of mass is the amount of gas it forms. But this really starts giving us a story, is the universe had to, and getting the idea, for us to exist, had to produce large mass stars first. And we go out and look, and that's what it did. It produced large mass stars. In fact, there was a tendency for when things first clumped together, that there was enough mass that the original stars were 100, 200 times the size of the sun. I mean, structurally, those type of stars can't exist now because they can't get that amount of pure hydrogen. They burnt really, really, really quickly, living only a few million years, 10, 20 million years. And in their cores, they produced all of these elements, and then they exploded, producing all of the other elements. That explosion sent gas out throughout the universe. It pushed gas that was stable together, and that clumped to form slightly smaller stars. And those slightly smaller stars were still massive compared to the sun, clumped together, exploded, produced more of the elements. And we tend to think right now that our sun is a fourth generational star. There were 3 or 4 stars that had to explode to produce the gases that made our sun. Well, those gases also hung around the outside of the sun as it was collapsing and formed the building blocks for what would be the planets. And so these explosions of stars left chunks of heavier stuff around them, and that heavier stuff is what made the planets and made you. All right, so a calendar of how all these events chunk together. I watched this calendar. It is a Carl Sagan video, but I'm going to break it down here. If we take all of time and we put it on a calendar, the Big Bang beginning at midnight of January 1st, then in the Milky Way forms in February. The Earth forms in September, and we're first seeing life on Earth in September. So think about the expanse of the time, right? We're not even really talking about the Earth forms. That's around the same time the sun forms. They're same process forms these two things. So I could say the sun forms. So you have to think of multiple generations of stars happening in each month up towards it. And then if we look at December, we have a Cambrian explosion of life, which is when life starts diversifying. Early life in September was single-celled. Here we see loads of different types of life form. And then the dinosaurs come out just after Christmas. And we ourselves don't appear until a few minutes before midnight. Dinosaurs are extinct on December 30th, and then December 31st, we usually say around 20 minutes to 15 minutes before New Year's, human beings as a species come around, and recorded history is like a fraction of this. And so this is what we can see by monitoring the Big Bang, right? Yeah, 9 p.m. On December 31st we begin. 11:58, modern humans evolve, so 2 minutes before midnight. 25 seconds ago, agriculture arises. 11 seconds ago, the pyramids are built. A second ago, Galileo and Kepler were about. And that's it. We're saying we take the entire history of the universe and we make it 1 year. Everything we know that human beings did exists within 25 seconds of that year. So what I'm going to do right now is I'm just going to be silent for 25 seconds. And I want you to think about everything that people have done and everything that you know about people have done. And if you take this year as being the history of the universe, you can cram the entire thing of human beings in that 25 seconds. So here we go. Things about moments of silence is they tend to feel longer than if you were measuring the time otherwise. So maybe that was a good reflection for the entirety of humanity. Um, this is the thing about studying these things that people tend to try to back away on. We want to elevate our position and our worth, or at least psychologically defend ourselves, saying we matter, and we do matter, right? Because if we also think about how rare everything you do is, right? And it's that rarity that I think gives it worth. All right. Planets form around stars. So we looked at how all the elements could get there, how the universe produces elements. Well, planets themselves are forming when stars form. The gas around stars collapses. And we actually have pictures now of star formation, early stars that are collapsing gas and just starting to ignite. And we can already see what looks like to be planet formation. In fact, I believe in this particular one, do I have it here? No, I don't. We have found an object that's kind of like a massive Jupiter that's starting to clear a planetary path around it. And we can see areas where the gas is being cleared or changed by different effects. And so this is gas falling in to make a star. And that gas will consist of all the elements that were from some exploded star previously. And what happens is it collapses together and it conserves angular momentum. Just like we were spinning that bike wheel around. If it was turning just a little bit, it's going to conserve that angular momentum. It's not going to want to turn in any directions. Remember, I spun the bike wheel and you tried to turn it in a different direction and it wouldn't want to. Well, that's going to happen to all the matter in here. It all wants to turn the same way it was initially turning. And so as it does that, it's going to collapse into a flat shape with the rotation in the same direction. It's going to prefer that same rotation. That's why solar systems and galaxies have a tendency to look like a wheel. That force you felt in the wheel, not wanting you to turn, not wanting you to move in the other direction. If a mass of gas has just a little bit of angular momentum, it's not going to want to travel in the places that aren't in the same direction. I shouldn't say want, right? It's not conscious, but that's what the laws of conservation of angular momentum does. And so it flattens into a wheel over time. Now within that wheel, all those pieces of gas, well, they have a smaller and smaller place to go now. So they start hitting each other. Sometimes they stick, sometimes they bump their companion into a different area. And that dust feels the radiation coming out, trying to push it further away. It bumps into each other, they stick together, it gets heated up, and collisions happen and they start forming planets. I don't worry about that. What ends up happening is the force of the radiation of the star starting pushes the lighter stuff further away, while the heavier stuff doesn't get pushed as much. So you see planets that have rocky, silicon-based, that's the moons. Let me go to our planets. go to. The rockier planets are towards the center, and the gassier planets are towards the outside. And it's because of this pressure of the radiation of the star pushes the gas easier and further away. And so our gas giants like Jupiter and Saturn and Uranus and Neptune are further away, and the rocky stuff that doesn't get easily pushed away are near the center. Now, the center of Jupiter probably has a rocky chunk very similar, well, it's probably been destroyed by pressure, but very similar to Earth. There's probably a solid core to the gas giants. And so these chunky cores pick up more and more stuff. The stuff on the further away has loads of gas to pick up around it because the star is pushing gas out, and we get something like a solar system. Now we have moons. Moons are rocky chunks that orbit planets. They all orbit in the same direction. And then we have asteroids, which are chunks of rocks that exist. They look like they could have been debris of stuff that should have been planets, but they didn't clump in with things. And there are loads of them. There's also a lot of them between Mars and Jupiter, because Jupiter's gravity probably stopped another planet from forming. So there's a chunk of stuff that could have been a planet, but Jupiter just kept kicking it, going, nope, this is my area, this is my area. But that doesn't mean that's the only place where asteroids exist. There's asteroids all over the solar system, and they have different orbits. We have comets, which are chunks of ice, gas ice, that are from far away, that pop in. And some comets we think might not even be part of our solar system. They're of the nearby material, and they drop in. And we have some questions about the Unami object that came through, was that a year and a half ago. All right. And so as comets get close to Earth, that ice melts, and we can see that ice melting behind them. The thing that we want to think about this formation of stuff, and the planets orbiting the sun, I'm done with this slide, I think. Yeah, I'm done with this slide. And I just want to, oops, cancel. Come over here. Sorry. Come over here. All right. 2 seconds here. This is, there we go. All right. And I just want to get an idea of what has happened and kind of put this all in a perspective. So we have some point in time, 13.8 billion years ago, where all the matter in the universe is in a single point. But that's not stable, right? You put everything in one place, and people and things are going to want to move about. The universe wanted to move about. So it started to expand. As it expanded, it formed hydrogen, mainly hydrogen, protons, and that formed hydrogen and helium. So most of the universe is hydrogen and helium, some beryllium and lithium, beryllium and lithium. And gravity started clumping those things together in galaxies. And the initial galaxies formed really large stars. And those stars start peppering out here. And the stars explode, throwing gas everywhere, creating more stars. And so we have this progression of time where we have a life and birth cycle. We actually had everything probably in what would be an ordered state, right? Everything in one place, forming a perfect ordered grid. It's probably the less chaotic. It begins expanding, and as it expands, things spread out. Right? That's what things tend to happen. But parts parts of them clump together. There's clumping. And you and I are these local little clumps of this initial displacement, or this initial displacement of everything being in an ordered space. And it expands out, forms stars, the stars explode, forming more stars, they explode, forming more stars. And in the process, we build a whole periodic table. All these forces and energies take these things and form slightly more complex things. One of the things that's noted, though, is that atoms have a tendency to decay. There's nuclear decay on heavier atoms. And the energy that has gone in to crushing together these atoms binds the nucleus, right? We'll have some neutrons, protons bound. This energy binding them is being pushed on by the protons trying to go apart, because they're the same charge. And static electricity is telling us things with the same charge are going to push away. So over time, radioactive decay is going to happen. And some energy. Right? And so atoms will tend to want to break apart. And so we have this thing where everything's getting further apart and all the atoms are trying to break apart. Now, physicists tried to look at the expansion of the universe models, and one model they had was what we're going to call a closed model. That the universe expands, it reaches a point of further expansion, but gravity takes over and pulls everything back. So this is the distance or the size of the universe, and this is time. And this was called a closed universe. And you could say, hey, everything gets back together, maybe whatever started this, it would repeat. There was hopes that it would be cyclic. And so they decided to go out and measure the rate of the expansion of the universe with supernova. Now the equations also have another solution, which is an open universe, where the universe doesn't turn, where gravity never takes over, it just slows it down. It slows down the expansion, and the expansion stops going so fast. And there is a third option where the expansion continues at a constant acceleration and goes fast. When they measured it, when they went out and measured it, this was the theory that scientists were looking to prove. In fact, they were actually looking to find the breaking rate of the universe, how quickly it would break and where this maximum point would be. Instead, they actually found out that the acceleration is increasing, and we're going much faster, like this. And so the modern idea of we wanted a closed universe, we like closed things, cycles of life, cycles of things, and we were looking for this, but observations are telling us it's going faster. Now, there is a lot of debate about this. A, philosophically, it's a hard thing to take that our universe is going to go further away. And B, the things we're measuring are really hard to measure. And right now there's a lot of revisitation of this observation. But two teams observe this separately of each other. So it's considered to be what we know now. We are trying to work our way to see if this is correct. If this is correct, though, philosophically, here's what's going to happen to everything. Over time, the galaxies are going to get further and further apart until you can't see them anymore. And then in the gravity that's holding the galaxies together, they'll collapse into black holes. The black holes will radiate away slowly through Hawking radiation, and eventually the universe will consist of atoms that are very far away from each other and getting further away from each other because this expanding is accelerating. Those atoms will radioactively decay until we just have protons. And the universe will be expanding so quickly that if this sends out any radiation, it will never get to another proton. There will be no way to transfer energy from one proton to another. and the electrons will exist in a gas between this that are also getting separated further and further and further. And this is called the heat death of the universe. Luckily, we're looking at, like, we don't get to this state for about 1 trillion years. 1 trillion to 10 trillion years. So when we stop to talk this thing about the philosophy of studying all of this, in light of all of this, right, with our best observations, we can say we've got about 1 trillion to 10 trillion years to figure it all out. Once we reach this point, we probably won't be able to hold things together. I find that as a challenge for human beings. Not as something bleak, but of a, like, if this is what it is, what can we be within it? I don't know. People always say I am a pessimist because I talk about the worst case scenarios, but I always find worst case scenarios as being like a challenge, because I actually do believe human ingenuity. If we know enough, we might be able to do something in light of all this. And so I look at this as a challenge. But I will say right now, there's people are re-questioning this. Right, we've had this thought for about 2 decades now, and people are looking at it, and newer measurements are maybe improving the model. And so maybe, hey, we don't get this. Maybe we get this, which does the same thing but much more slowly. We'll see.